Hello, everybody. It's my pleasure today to welcome Michel Herquet for his keynote on open source tools that could be used in data science project and artificial intelligence project. This lunch talk takes place in the AI4GOV track of AI for Belgium. So it's AI dedicated to the public services. And unfortunately, we have to postpone the hackathon, but we have kept this lunch talk so that you can have a first insight into this broad world that is open source software for AI. I just have to mention that we will organize the Belgian AI Week from March 15 to March 19. You are more than welcome to participate. There will be keynotes, there will be thematic workshop, there will be publication of reports on AI in Belgium, and there will be also citizen debate. You are more than welcome to participate to it. But now, let me introduce Michel. So you have to know that we are recorded. So please, yeah, you have to know it. And thank you, Michel, for being there. So you have an academic background in theoretical physics, and you have received a PhD in particle physics from UC Louvain before working as a postdoctoral researcher abroad. Your research work was mainly focused on the development of advanced Monte Carlo simulation for Higgs boson discovery. So there are many physicists that enter now into artificial intelligence because you have a huge mathematical background and knowing well how to manage the data. In 2010, you joined McKinsey company as a junior associate and work on projects in strategy and marketing sales for clients in various industries. In 2012, you co-founded B12 Consulting, an IT service firm based in Louvain-la-Neuve, specializing in custom software development and data science projects. Since then, you have been leading dozens of advanced analytics and AI projects for clients in many different industries. You also regularly teaches physics and management university courses, both at elementary and advanced level. And at a more personal level, Michel, you are passionate about photography, social science, board games, and new technology. It's really a pleasure to have you here. For the audience, if you have some question, please ask it in the chat. Michel will talk for 40 to 45 minutes, and then we will have a Q&A. So Michel, the floor is yours.
Thanks so much, Nathanael, for the very nice and very kind introduction. So it's really my pleasure to be here and to have this opportunity to talk about this topic, which I'm quite deeply passionate about, which is, well, two topics actually, which I'm deeply passionate about. On one hand, open source software, and on the other hand, AI and data science. I was thinking, actually, I didn't know that I was going to make such a nice introduction, so I thought that maybe it would be nice to give you a little bit of background about myself so that you understand why I'm talking here today, and also so that you better understand what is the connection between my background and open source software. So, well, you have to know I'm born in '82, and actually '82 is 1 year before the new project, which is the project within which the free software concept originated. So I was essentially born at the same time as the notion of open source software. And I think this notion really, I mean, I closely lived with this notion for many years and until today. In the 80s, when I was still a kid, I had my first coding experience transcribing some at that time printed open source basic programs. So I mean, people were actually buying magazines where in the middle pages of the magazine Well, obviously you can find many things in the middle pages of magazines, but at that time, when I was a kid, I was interested in reading the open source, well, the printed open source. By definition, they were open because, I mean, you could read it. Basic programs that were printed and that you could actually transcribe manually into some computer. And my dad at that time had a VIC-20 computer, a kind of a Commodore 64 computer, and I was really into transcribing those basic programs, which were mainly games. And then a little bit later on, in the 90s, I started being a little bit more serious about programming, mostly by learning how to hack 3D video games source code, which was not officially open, but at that time it was relatively easy to find, some copies of the code of many different 3D video games. So it was nice to learn programming by understanding how the code was structured and was written and trying to modify it. And then later on, I started my career in academia. I did, as Nathaniel mentioned, I mainly work in physics, and during those wonderful years in academia, I spent a lot of time developing a software called MathGraph, which is still today one of the most widely used open source simulation tool in Python. So again, I mean, I was exposed to open source by actually being in charge of a relatively large open source project in academia. And then, yeah, sometimes something like 10 years ago, in 2012, I co-founded B12 Consulting, this service company Nathaniel was mentioning, specializing in software development and data science, mainly using open source tools. And so once again, my road crossed the road of open source project, and I think it gives you a little bit of context, and you can see the little pictures I put together on the left. You can see me as a cute little kid over there in '89 in front of this VIC-21 computer with my sister, and then with one of the co-founders of B12. At the time, we were peer programming, and okay, we didn't have much money at the beginning of B12, so it was either using the electricity for the computer or using the electricity to heat the room, and well, we decided to go for the computers. And the last one is a picture we took 2 years ago of the B12 team. It's much bigger now, almost 30 people, but it gives you a little bit of context. So I'm not going to speak anymore about myself, but maybe just a disclaimer about the talk of today. I just want to emphasize the fact that this overview will be quite opinionated, which means I'm not necessarily going to try to be objective. I'm going to review the tools we are really using almost every day. And I didn't try to make a really objective review of all the possible open source tools you could use. There are so many, there are probably thousands of open source tools literally you could use, but I've tried to remain relatively selective and relatively focused on a few of them, which I believe are the most important one when you enter the field of data science. I will also be forced to stay rather superficial because, and for example, I won't do any hands-on session, even though those are probably the best options to really learn the tool. But we have so many things to discuss that I don't necessarily, I won't necessarily have the time to enter into too much detail for each of them. But you will see at the end of the talk, I will give you, directions about how to discover them more deeply by yourself. The last thing I want to mention is that there are always debates all the time about the fact that artificial intelligence is not data science and data science is not machine learning, even though machine learning is part of data science work. And you could also say that those are not at all equivalent to data engineering or MLOps or BI or whatever, all those different words covering different realities. For the sake of the argument, for today, I will stick to data science, even though the call for I use the word AI in the title of the call for marketing reason, I would say. But as you know, mostly in Belgium, I mean, people are actually doing data science nowadays. So what I will cover, as I explained in the short summary, I will actually explain mainly the use of open source tools in the context of data science engagement. Okay, so why open source in 2021? I think open source softwares really have a long list of very nice qualities and very nice strengths that are actually difficult to find in other type or in other licenses of software. First, transparency. The fact that you can always go back to the code and see what's going on in there. The support, and I know that sometimes people are a little bit worried about the actual support you will get by choosing, after choosing to use an open source tool. But the reality is that for most of the tools I'm going to present today, you have a huge community support with highly dedicated development teams who are very open to answer your question most of the time. And also, more important, a vibrant user community. And all those users probably face sooner or later the same difficulties as you did and are there, and you can interact with them and you can try to solve solutions together because the code is open. Interoperability, the fact that open source tools have, I would say, to survive, they are forced to interact with other tools. It's also true nowadays for proprietary tools, but it's even, I think, more true for open source tools. The fact that interoperability, is mandatory really implies that those tools have to implement really good standards, and it really helps having, I would say, a toolbox of tools that can nicely interact one with each other, and we'll see a lot of examples of this later on. The security, the reliability, the quality, I think are not to be proven anymore. And if you just have to cite, one of the operating system which is considered as the most one of the safest one, at least nowadays, Linux, that's clearly one of the flagship of the open source community for that. Innovation and evolution opportunities. Obviously, the fact that the code is open makes evolution and innovation much easier. It makes the job of people who are trying to contribute to the project much easier. Stability, even though that might sound a little bit counterintuitive, because sometimes people are a little bit worried about the fact, that open source code, they might not be maintained in the long run, or the development team might change too much, and they might create changes which are not backward compatible, for example. And actually, in practice, when you see all the open source tools I'm going to talk about, that's just not true. I mean, most of those projects are, remarkably stable in the long run. Easier hiring. I mean, if you're in charge of a development team like me, the fact that finding developers and data scientists who have been trained on those open source tools is a big advantage. And clearly, I mean, when people are students, they don't necessarily have the money to buy proprietary tools or expensive platforms. So the fact that they most likely first discovered free open source tools is also, I think, one of the reasons why it's easier to hire developers with this knowledge of open source tools. And I would say that nowadays, and I think that many of you already know this, it simply became the norm. I mean, most projects that you can see, even in the industry right now, are either released as, for the big players, I'm talking about the GAFAM, for example. Most the tools those people are producing nowadays are, at least in a large extent, released as open source for all the good reasons I've mentioned. And I would say that nowadays, choosing a proprietary product is probably more an exception than choosing an open source software, at least for the applications I'm going to talk about. So, what is open source about? I'm not going to enter into any detail in there because I'm not a lawyer and I'm not a specialist of open source licenses. But open source essentially means that you can access the source code when you can access the software. So if you can access and use the software, that means that by definition, you should have access to the code at the same time. And in terms of licenses, you can essentially distinguish two big categories. One category is the category of permissive licenses. That's by far the most common nowadays. And you have the other type of licenses, which are called copyleft, sometimes called viral also. The big difference being that the permissive license, the tools with a permissive license you are allowed to use those tools in the context of proprietary closed source project. As you can see here, it's written, true for can be used in proprietary or closed source project. And for the copyleft one, since the license is viral, you actually have to propagate the license of the tool you are using to your own developments, which means that the tool you are building also has to share this license. There are there are a few exceptions to that, especially with LGPL's licenses, but that's the spirit of it. So you should make this distinction, and then inside those, I would say, two families of licenses, you also have some variations, for example, between BSD, MIT permissive licenses and the Apache permissive license. The main difference being related to the protection for patents, which is embedded into the license itself. Okay, and here below you can see that there are a few examples of relatively large open source projects which are using those different licenses. You see a red box here. I call this pro tip. Those are a few tips and tricks I'm going to share with you for the different things I'm going to talk about. And for this one, I think the big advice you have to remember is that open source license is quite a complex matter actually, and you should never hesitate to ask for professional legal advice. It's better to ask for an advice that might cost you a few €100 than actually taking the risk of, for example, using a viral license and ending up being in a bad position in terms of opportunities, for example, to release your code as a proprietary software, if that's what you want to do. Open source for data science application, all the qualities I've mentioned for open source are definitely important qualities in the context of data science applications, but I would say that some of them are quite critical. For example, the transparency. I think that nowadays, I would say that no serious innovative data science work can afford to rely on black box proprietary algorithms. So if you are building a new innovative solution for a client, whatever this client is planning to use it internally or to release it as a proprietary tool or maybe as an open source tool, it's very difficult to build a solution which rely even partially on a black box proprietary algorithm. The reason being that for both methodological and ethical legal reasons, it's difficult to tie to your future in terms of developing some new methodology or some new software and saying that this part actually we don't necessarily understand what's going on in there. Yeah, it might work, but maybe it doesn't work, and the big issue is that you might not necessarily know when it will work and when it won't work, and as soon as it will start not working, because there are always limitations to all the tools we are going to use, it will be very difficult for you to understand why it's not working anymore and how to possibly fix that. And actually you won't have the possibility to fix that because the tool is proprietary. So I think that for this reason, especially in data science, where at least that's my that's my point of view, in data science we have to be very transparent about in how we are building the tools we are actually providing to our clients or to our customers. I think this notion of transparency, which is inherent to open source tools, is really crucial. Continuous development and support. Data science is definitely a very fast-moving field nowadays, with cutting-edge technology of yesterday becoming really mainstream today. So the fact that you have all those vibrant community, both of users and developers for open source projects, really make this fast evolution possible. And it's actually very often the case that we can see that proprietary projects, even though they can be innovative, it's sometimes difficult for them to remain innovative in the long run, whilst some very famous open source frameworks or tools succeed doing that. Interoperability. Most data science applications rely not on a single, but on a large set of interconnected tools. So the fact that most of those open source tools have to implement, I would say, open standards, because by definition they have to interoperate with other tools to be useful, is really a big advantage, because sooner or later you will have to replace some parts of the solution you are building, and the fact that you are using open source tools will really be an advantage in the sense that you are also using open standards to make those different tools interoperate. Okay, but let's deep dive into the actual content of this presentation, trying to review, unfortunately, a little bit quickly, but I think it will be relatively horizontal and general enough to give you a good picture, to try to review different tools that we as data scientists are using almost every day. And obviously, I have to start with the programming language. I think Python is probably the tool I would choose as the main. Python is the language I would choose as the language of choice for data science, mostly because it really became the lingua franca for data scientists nowadays. For those of you who don't know, Python is an interpreted high-level and general-purpose programming language, which has essentially, from my point of view, two advantages. First, it's highly readable. It has been designed to be highly readable, in particular because it has a significant use of indentation, and also because it's a modern programming language, or at least relatively modern, that supports multiple programming paradigms, including procedural, like most programming languages, but also object-oriented and functional programming. But its first strength, it's not really in the language itself, it's in the ecosystem that comes with the language Python. It has first a comprehensive standard library, so the Python language itself is bundled with a standard library of tools, which is already very powerful by itself. But more important, it gets complemented by a huge number of third-party libraries. And those are the libraries I'm mainly going to talk about today. The language itself was released in 1991 under the Python Software Foundation license, which is essentially a so-called BSD-style permissive license, so it's perfectly open source. And it is nowadays distributed under different ways, but one of the user-friendly distribution is called Anaconda, and that's the one I would recommend you to use if it's the first time you are trying Python, and it's available for most operating systems nowadays. In terms of competition, well, you should definitely mention R, which is still dominant as the language of choice for data science in different specific industries. I'm thinking, for example, about banking. I'm thinking about the pharma industry, essentially industries where you have a relatively strong SaaS legacy. So R is definitely a good choice. From my point of view, the main reason why we choose Python, we prefer Python over R where we have the opportunity, is mostly because of the ecosystem of Python, which is more rich and which is not only limited to data science and data analysis work. R is really focused on data analysis, while Python is more of a generic language that can also be used to build data engineering application, web services, and things like that. Scala, which is a bit more recent, which might have the advantage of being statically typed for some programmers, and it's definitely faster because it runs on a JVM. And in terms of disadvantages, I would say it has definitely less third-party libraries for achieving data science work, for completing data science work, and possibly Julia, but I would put this on the side. My recommendation for Python would be, don't be fooled by Python being seemingly having a seemingly smooth learning curves. It's actually more complex. I mean, you might have the impression that Python is relatively easy to learn, and that's true. It's easy to learn, but it's relatively difficult to master. So I think it's a good tip to tell you to really spend some time, if you are not familiar with this language, to spend some time really understanding the language itself, the programming language, and understanding its advantages and possible weaknesses. JupyterLab is what we call is providing you with a solution that we call notebooks. And those notebooks are essentially a convenient way of using Python as a scripting language and seeing immediately the result of your calculations. So Python can be used to build softwares, complete softwares, but it can also be used in a kind of interactive mode. Maybe some of you have used in the past things like Mathematica or MATLAB, and Jupyter really allows you to have this very interactive editing of your source code and saying immediately, for example, being able to see the value of some variables or to see immediately the result of some plots and so on without having to repackage it as a software that you run independently. But you have to be careful that interactivity is also the weak point of notebooks. For example, it's very difficult to run tasks asynchronously. Long-running tasks are difficult to handle in notebooks. Sometimes the cell order can get mixed up. So, I mean, if you run a cell and then run another one, you could be confused with the state of different variables along the way. And all this really actually makes long notebooks very difficult to handle and also quite difficult to share inside the team, because versioning of notebooks is very difficult when they are shared. It's very difficult to merge modifications to notebooks. So notebooks are really interesting, especially for, I would call, experimental data science work, but you should avoid using them for building actual products. And that's the pro tip, essentially. I mean, you can definitely use notebook, and it's even recommended to use notebook for interactive manipulation and visualization of data, for example, but you should probably try to avoid using notebooks for building serious softwares. In terms of alternatives, well, most alternatives are related to professional editors for the code, what are called IDE. Such as, for example, PyCharm for Python or VS Code. And since last year, VS Code is actually also implementing a way to see and run interactive notebooks. So you might also consider this solution to run interactive notebooks from inside Visual Studio. Numpy. So Numpy is actually a fast array manipulation library for Python. So Python being an interpreted and dynamically typed programming language, it is also quite bad at manipulating large arrays of number. That's something you would, that you could very efficiently do in low-level languages such as C or C++, for example, but which is quite difficult to do. Well, it's not difficult to do, but it might be not performing well if you try to do this naively in Python. So Numpy helps solving this problem by implementing native multi-dimensional array types and all the associated manipulation methods, for example, in the spirit of MATLAB. So essentially, Numpy is a way to define multi-dimensional arrays of numbers and manipulating them very efficiently while still using Python. It typically leads to very impressive performance improvement, typically over the 100. And the end results when you are using Numpy properly for doing calculations on large arrays of numbers is that you end up having a performance which is quite similar to what you will find with low-level languages such as C or C++ or other statistically typed programming languages. Numpy is actually the underlying low-level calculation technology used in almost all more evolved data science libraries I'm going to talk about. So one of the good reasons to learn Numpy is that it's definitely a building block of almost all the other libraries I'm going to talk about. It was released quite some time ago in '95 under the permissive BSD license. And there are not that many alternatives in practice. That this Numpy library is used so heavily that there are not that many alternatives. One could cite Numba, which is a way essentially of compiling Python, so it improves the performance very significantly, and CuPy, which is a GPU kind of accelerated Numpy. And you see here an example of how to define and how, for example, to define some scalar product between two arrays in Numpy. The pro tip here would be, if your Python software or your Python script is slow, then you should definitely look into the Numpy documentation and try to make a better use of Numpy. Because most of the time, what we have seen, is that when people are complaining about the speed of Python, is because they are not using Numpy the right way or not using Numpy at all while they should. Okay. Scipy, which is another very fundamental component of most data science engagements, at least for us, I would say it's your first guess solution for most statistics and numerical analysis challenges. So Scipy is a very large, one-size-fits-all kind of library built on the top of Numpy, which aims at solving quite a lot of common statistics and numerical analysis challenges. It covers, for example, signal processing, integration, differentiation, solving ordinary differential equation or partial differential equation. It has a lot of different optimizers, statistical function, clustering methods, and so on and so forth. It's very reliable. The methods that are implemented are extremely well tested and reasonably fast. It's quite very often a very good choice for first prototypes. It's quite limited in scope. I mean, it's not covering that many things. It covers, I would say, all the essential of numerical analysis that you would find in a typical book on numerical analysis. But it's enough for many, what I would call back of the envelope kind of calculations. It has, again, no real alternative as a single library, but you have plenty of specialized packages that might implement some of the tools you would find in Scipy. For example, Stats Model for statistics or Gecko for optimization. They do better most of the time than Scipy, but the big advantage of Scipy is having this single library that covers all those different needs in a nice integrated way. And the pro tip is, yeah, if you don't know where to start for some numerical analysis problem in Python, Scipy is probably a good starting point. Here you have an example of a classical statistical test, independence test, chi-square independence test that you can run very easily in a few lines of code with Scipy. Here come pandas. So pandas is probably all you will ever need for what I would call in-memory data frame manipulation and analysis. So what do I call data frame? It can be seen as a kind of in-memory database object, including a big table, a big Excel table, if you want, that you can load in your memory, and that contains different types of structured data. You can find, dates, numbers, strings, text, and so on. And together with the relevant indices, for example, to access any item or any row or any column very efficiently in this data frame, and to run quite a few manipulations of the data frame. For example, selecting or merging two data frames on a given key, or executing things like pivot tables, right? In Excel, you have those pivot tables kind of operations, and you can do the same in pandas. Actually, the number of manipulations the number of things you can do manipulating data frame is fantastic. I mean, relearning pandas is really going to help you being much more efficient as a data scientist, especially for everything related to data preparation. So obviously, you are not necessarily going to run very advanced analysis with pandas, but what you are going to do is essentially being able to start from a given data set and being able to manipulate this data set to kind of massage the data so that it ends up being in a format that you can use in more advanced tools or algorithms later on. It can be extended to allow for parallelization. So if you have very large data frame that could not be stored in memory, you can use tools like Dask or Module, for example, to split those data frame and start doing parallel work for manipulating those data frames. It was first released in 2008, also under a permissive BSD license. And again, there is no real alternative for the library itself, but you can probably achieve similar results either directly by using the right SQL query, or using tools, more big data oriented tools such as Apache PyArrow in PySpark, Arrow for Spark or PyArrow for the Python version of those tools. The pro tip is that if you end up doing some manual iterations, for example, on the different columns or the different rows of your data frame, that probably means that you should spend more time learning pandas, because pandas is really implementing all those fantastic methods that that will help you doing all those manipulation, not only very conveniently, but also very efficiently, because under the hook, pandas is actually using Numpy for plenty of calculations. Matplotlib, that's the one that comes for data visualization. I would say Matplotlib is kind of the de facto standard plotting library for the Python programming language. And it has to be known that there is kind of a lack of a very good visualization library for Python. And that's one of the areas, for example, where R has a big advantage, at least from my point of view. ggplot, which is one of the tools that is used for data visualization in R, is, from my opinion, actually superior to what you could find in Python. But I would say that definitively Matplotlib is probably, it's definitively the oldest, and it can be considered as the most reliable and flexible data visualization library for Python. But it can be sometimes cumbersome to use, especially for very complex plots, and the default look and feel might seem a bit dated. I mean, sometimes it looks like your plot is coming from the 90s. If you want to improve on that, you can use a tool which is called Seaborn, which is just a layer on the top of Matplotlib, which helps building nicer Matplotlib plots from out of the box. There are also other options. I would say, for example, Bokeh, which is a library that helps for interactive visualization library. So it's a visualization where you can actually, for example, tune some parameter and see the effect of tuning those parameters on the plots. You have also something called Plot9, which is kind of an implementation of ggplot under GPL license. So, for example, here you have to be careful because that's a viral open source license that could contaminate your own project if you are in a proprietary project. But most important, and what I usually advise people, newcomers to the field, to do is definitively, including with Matplotlib, don't try to invent the wheel. There is this web page where on the Matplotlib website where you have plenty of examples of libraries that you can use, plenty of examples that you can use and tune to build your own plots that really look not necessarily terrific, but at least good enough. Okay, so now we know how to manipulate large arrays. We have Scipys to do all the classical scientific calculation, numerical analysis things. We have pandas that really going to help us loading and in memory and manipulating very efficiently in memory large data frames. We know how to make some nice plots. Now we have to jump to the actual meat of the presentation, the tool we are using for machine learning and deep learning needs. Scikit-learn is sklearn. We usually call it sklearn. It's what I would call the Swiss Army knife for all classical machine learning tasks. So if you don't know it yet, I really strongly encourage you to discover this wonderful piece of software called sklearn. It's a free software machine learning library for Python, which has been designed to interoperate very nicely with Numpy and Scipy. It is a quite generalist library, which means it does a lot of different things, and it doesn't necessarily try to be extremely good at doing one single thing. The goal of sklearn is really to do a lot of different things. It does classification, regression, clustering, and it includes tens of different algorithms from supervector machines, random forest, gradient boosting, neural nets, at least those with no dense layer. So I'm not necessarily talking about deep learning here, but I would say simple neural nets, k-means, and things like dbScan and so on. So it really includes plenty of nice classical machine learning algorithm that should always be your first choice when you actually try to solve a simple machine learning task. Its main strength for me is really its very strong architecture, which is shared by all the algorithm implementation, and it has a very large panel of integrated helper functions. For example, pipelines to extract features for dimensionality reduction, for cross-validating your models, for hyperparameter tuning, and so on and so forth. So it is the combination of a very strong architecture, a lot of helper tools, and all those things can be orchestrated using pipelines so that you can remake all those algorithms work very efficiently all together. It was first released in 2007, I believe, under a permissive BSD license, and it is mainly maintained by a group of French researchers that Nathaniel can talk about if he wants after this code. Again, no real alternative in the sense that it's probably the most well-known and the most the one with highest reputation, I would say, generalist machine learning library in Python. But as I've said, there are a lot of other libraries which are implementing more deeply specific algorithm. Think, for example, about XGBoost for gradient boosting. Pro tip, it's actually not so difficult and rather a good idea most of the time that if you are trying to implement your own machine learning algorithm, to try to implement those algorithms to fit into the sklearn architecture. Because if you use their paradigm in terms of structuring your algorithm, it will really help to interoperate your algorithm with all those existing chains of validation, of dimensionality reductions and so on, pipeline that you can reuse. Here comes TensorFlow. I guess most of you have heard about TensorFlow. It's an established framework to build deep learning models, and I assume also that most of you have learned about deep learning. It's a machine learning library with a very strong focus on training and inference of deep neural networks. It does a few other things than neural networks actually, but probably it's most well known for being very efficient at building new deep learning models. Since it's version 2, it comes bundled with Keras, which is actually an interface between TensorFlow and Python. In the past, you had to download the two different packages and to make them interact. Now, Keras 3 comes bundled inside TensorFlow itself. It is very highly optimized to be trained on GPUs and TPUs, so specific type of processing unit for doing tensor calculations or matrix calculations. And it allows execution on very different environments. For example, you have TensorFlow.js to execute code inside web browsers, or TensorFlow Lite to execute code on mobile or edge devices. It was originally developed by Google back in 2011, if I'm correct, and released as an open source project in 2015 under, again, a permissive, this time Apache, license. Its most notable competitor nowadays is definitely PyTorch, which has been introduced by Facebook, which is gaining a lot of momentum, I have to be honest. Recently, we are still using at B12 TensorFlow, but PyTorch is definitely worth your interest, especially thanks to, I would say, a more dynamic approach to graph topologies, why because of its combined nature, TensorFlow has a more static approach to graph topologies. And here you have some sample code. You can see that in a few lines of code, you can relatively easily build a new deep learning model. The two last libraries are more focused on specific applications. OpenCV, the first one, it's a mature toolbox for building computer vision applications. It's a relatively old library, over 20 years old, first introduced by Intel under the permissive Apache license. It implements a lot of low-level functionalities for image editing, for example, detecting contours on images, for doing some matrix manipulation exercise and so on, for applying filters on your images. But it also does nowadays a lot of, it implements a lot of high-level machine learning-based applications with pre-trained models, for example, for face and gesture detection, for stereo visions, for all those kinds of very advanced computer vision tasks that where you really don't want to reinvent the wheel. So I strongly encourage you to use OpenCV for those image manipulation tasks. So it can be used both as a complete, I would say, out-of-the-box solution. So you just take, for example, face recognition algorithm, and you can apply it straight away inside your own application. But it can be used, and that's the way we typically use it at B12, as a toolbox library for building new algorithms for computer vision. The main alternatives for generic image manipulation tasks are scikit-image and Pillow, probably less powerful than OpenCV, but interesting nevertheless, and a lot of other libraries for very specific applications. Think, for example, about Open3D for 3D data processing. Pro tip, it's a good practice, whatever you try to do in computer vision, I think it's a good practice to always have a look at OpenCV to see if they are not already implementing what you're actually trying to achieve. Last but not least, Spacey is a modern library for what is called natural language processing. So for all tasks in machine learning related to natural language processing. Obviously, it's open source. It provides a little bit like OpenCV. The idea is that it provides both the low-level methods to handle standard NLP tasks like tokenizing, removing stop words from your sentences and things like that, but also much more complex one. Think, for example, about summarization. And in particular, the nice thing with Spacey is that it comes, it allows you to connect in a very efficient and intuitive way to statistical model trained by popular deep learning libraries such as Tensorflow, PyTorch. It supports nearly 20 languages, and it comes bundled with a lot of different pre-trained models. Think, for example, of transformers model like BERT, which have been shown to be extremely successful, for example, for tasks such as summarization. It was released in 2016 as an open source project, so it's quite a recent project compared to the other one under the permissive MIT license. The most notable competitor in the Python world is probably NLTK, which is older and more oriented towards research and teaching, but that we were intensively using prior to the release of Spacey. Pro tip, modern deep learning approach to advanced NLP tasks really require a huge amount of data. So my recommendation over there would be to always consider transfer learning solutions, meaning to start from pre-trained model where you tune or you add your own data set of text to actually improve the operation, improve the accuracy of those models on your particular data set, and not try to retrain those models by yourself, because usually the underlying data sets are really huge to achieve good performance. And here comes the final words. I think I'm almost perfectly on time. I'm sorry if there was a few questions, but maybe we can take questions right after. I actually cannot see the questions on my computer right now, but I hope we'll be able to take some after that. So what I've tried to achieve here is really a short overview. I could not be complete, but I try to cover a central but small, and you have to understand it's quite a small part of AI and data science project. Notable omissions, for example, would include tools related to data engineering, software development. I mean, when you have your ML tool, how do you deploy these ML tools? You have all the ML ops tools related to that, AutoML, everything related to automated machine learning kind of task, UX, UI software frameworks. So I put all this aside to really focus, I would say, on the core of the work of data scientists, but you should always think that you also have all those other needs that needs to be covered, and there are open source solutions for doing that. It might be intimidating to start working with open source tools, essentially because you might think that, you know, it's not that easy to find documentation. It's actually not true anymore. My personal advice as a work plan, if you have never tried to do data science with this open source Python stack of tools, would be first to start by dedicating some time to learn the Python programming language seriously, including Numpy. That would be the very first step. The second step, when you are more familiar or you feel familiar enough with the Python programming language, will be to move to a kind of hands-on introduction, a little bit horizontal, to the most commonly used library. And this book called Hands-on Machine Learning with Scipy and Tensorflow is exactly about that. That's really a book which is focusing on giving you a very horizontal overview of almost all the tools I've mentioned in this talk. And the last one is learn by doing. Pick up a real-world challenge, not a Kaggle contest, I mean a real-world challenge, and work on solving it by identifying and learning to use various libraries. And get support. That's a big advantage of open source. The availability of the community, the availability of people and users actually using the same tools as you. Even the developers of the tools I've been mentioning are sometimes remarkably open to questions and remarkably available to answer your questions, participate to meetup events, rely on your car expert, rely on the AI for Belgium community to help you with all those questions. And that was my final word, and I pass the mic to Nathanael.
Thank you so much, Michel, for this fascinating nutshell of overview of what we can do with that. So there are many questions. I'm not sure we will be able to answer all, but we will report and maybe give the answer written. By written, but okay. The first question: there are many technical persons also in the room. So what about community edition? Not OS, but for example, Neo4j.
Yeah, that's a good question. I mean, as soon as you can, I mean, depends a little bit what you call community edition, because I'm not sure there is a common necessary understanding of what you call community edition. It depends on plenty of different, I mean, every single tool would call its community edition in a different way. Community edition doesn't necessarily mean open source. It means that you can use it freely under certain circumstances. To me, the fact that you really have access to the source code is one big advantage. So I would say that if you can access the source code, then I would qualify it as open source, and you have different variations of open source code. But if you cannot access the code, whatever if it's free or not, it doesn't make a big difference. The point is that you are losing some control. I mean, there is no way you can see what's going on under the hook, and that might end up being an issue. Not necessarily. I mean, I'm not saying you should not use a proprietary tool. Sometimes it's a good idea, but I think that having access to the source code is still a big advantage.
Okay, thank you. There is a general question, less technical, but very important, because you talked about transparency, and yes. They say, so one question is, okay, you talk about transparency, but what's do the buzz for the moment? It's neural networks, deep learning, that are quite black boxes. So is there a part?
That's a good question. I mean, there are different levels of what you call transparency, right? But imagine that the tool you are using not only is using a deep learning model, which is by itself difficult to understand and difficult to interpret. I mean, there are methods for that, but that's beyond the scope of this talk. But at the same time, it's using a training algorithm for which you cannot even access the source code. So not only you don't understand the resulting model, but you don't even understand technically where it's coming from. And that's, I think, I would say, a double level of complexity in terms of transparency. So I would rather rely on open source, open source frameworks for building deep learning models.
Okay, thank you, Michel. I have so many questions. I will pick another one about the interoperability, because you say, okay, it's quite conditioned for open source, but there are many advantages of open source software, but is really interoperability the main one?
Yeah, so that's a good remark. I mean, is this really a must-have for open source tools to be interoperable? Probably not. I mean, you can definitely build your own open source, software which is not interoperable with anything. But the point is that it's most likely a condition for being an open source tool which is which is there to stay for many years. So if your open source tool lives in its own life without trying to be interconnected with other softwares, I believe that most likely the lifetime of your project is going to be quite limited. For most of the projects I've presented, they have a lifetime of about almost 20 years. And I think it's a good proof that using open standards, like almost all those tools do, is probably a good opportunity also to make your open source software usable in different environments. So I agree that that particular interoperability is not necessarily specific to open source. I mean, you can have proprietary software which are perfectly interoperable with other things. But the nice thing also with open source is that it makes interoperability a little bit easier, because, for example, if you can look at the code, you can understand how the software is, I mean, you can better understand the formats in and the formats out, for example, by just looking at the source code. While if the tool is proprietary, you have to rely on the documentation, and you have to, for example, to rely on the fact that the documentation is up to date, which is not necessarily the case. While at least for open source tool, you can run into the code and see exactly what's going there in terms of interoperating the software with your own software. So I still think that open source as an edge in terms of interoperability, but I agree that it's not necessarily the most striking feature.
Yeah, I have a real technical question for geographical analysis. Would you purely use Python pandas and GeoPandas, or combine Pythons with an external database like PostGIS?
It depends a little bit on the use case. So I cannot really answer that question for any use case. I would say for quick back of the envelope analysis, I would stick with pandas and trying to use all the surrounding geographical data analysis frameworks that can be used directly into pandas. But it's true that if you have large amounts of data, then you have to rely on other specialized big data tools for geographical data analysis. So depending on the use case, you will rely either on a restricted solution or on a more extended one. Yeah.
Yeah. Another quick question. It's about NLP text annotation for novice. Do you have something to propose?
Yeah, there are plenty of tools. Actually, the best one I've seen so far, I discovered it quite recently, and I think, but I cannot figure out the name by heart anymore. So I suggest I can answer that question remotely, because I have to find the name. I have to ask to the NLP experts locally what's the best solution they are using right now. But I know there is quite a good one open source right now.
Yes. Okay. Maybe a last question because it's really interesting. It's about should we oblige the civil servants, especially in this federal service, to create open source software? Do you think it should be compulsory as a general rule that software created with public money is available to everybody?
Yeah.
And what do you think of AI4EU initiative, for example, or scikit-learn?
I don't think you should oblige anybody to do anything, because that's the wrong way to go. But you should incentivize people to do it. So I would rather incentivize strongly people who are, delivering new projects or sharing their code in an open source way by having access to different subsidies, for example, of having access to other platforms. But again, I would not oblige anybody to do those kind of things, because I think people are trying to do their best with the tools they have access to. But I think that open source tools don't have probably enough visibility in public services. That's my impression for the projects I'm involved in. And maybe they should be more incentivized. I mean, people should be more incentivized using them. This is correct. Yeah.
Thank you so much, Michel. Would you be willing to do a more specific session on NLP or things like that? We will.
I'm not of the NLP experts, but I definitely can ask a few guys over here to give a session dedicated to NLP. I would be extremely happy to organize that.
Yeah. Okay. So yeah, it's a broad community. So if someone in the audience will also maybe present something during this track, you are more than welcome to propose. I thank you very much, Michel. I think there were many participants, about 100 present here today, and I say goodbye to everybody and see you at the latest during the Belgian AI Week from March 15 to March 19. But we have already some even before. For example, AI for Health on March 4, that will be also passionating. Bye-bye, everybody.
Bye, everybody. Thanks so much.